Welcome to This Explainer. Today we're looking at something that is literally hiding in plain sight in pretty much every industrial facility, refinery, and power plant on the planet. If you've ever walked through one of these massive spaces, you've definitely seen miles and miles of steel piping just running right above your head. And it looks entirely static, right? It looks simple. But beneath that stationary steel surface, there is this fascinating, deceptive complexity. We're going to uncover the hidden battle between physics and economics in industrial piping design. Which really prompts a seemingly simple question. How hard is it to hold up a metal pipe? Honestly, on the surface, it sounds kind of like a joke. You figure out how much the pipe weighs, you stick a piece of metal underneath it, or, hang a rod from the ceiling, and you call it a day. Boom, done. But as we're about to see, when you start throwing intense heat, heavy industry, and, let's be real, tight budgets into the mix, holding up a pipe becomes one of the absolute most intense mechanical challenges an engineer can face.
Okay, let's dive into this and solve this engineering puzzle. We'll start with 1, the dead weight dilemma. Then 2, the thermal growth twist. Moving on to 3, pulleys and counterweight fixes. 4, constant effort hangers. And finally, 5, the spring solution.
All right, section 1, the dead weight dilemma. Let's start with our baseline setup here, which is just carrying the dead weight of a pipe in a completely cold system. Gravity is pretty much our only enemy here. If a piping system just sits there at room temperature, our lives as engineers are actually very easy. You just run a dead weight analysis, figure out the load, and simply slap a rigid rod on it to hold the pipe up. Designers can locate these deadweight supports super easily using standard tables and charts. It's basically a set it and forget it situation. This rigid support doesn't move, it doesn't flex, it just stubbornly holds exactly the weight it was designed to hold. But why do we care so much about keeping it simple? Well, because engineering isn't just about physics, right? It is absolutely about economics too. Look at the massive price difference between the solutions here. A typical rigid rod hanger for an 8-inch high-temperature pipeline, throwing in all the hardware, is going to run you about $600. But a spring hanger? That will double your cost to over $1,000. And a constant effort restraint? Wow, that shoots all the way up to over $3,500. So we're talking about massive financial stakes attached to these supports. Bottom line, if you can get away with using a cheap rigid rod, you absolutely use a cheap rigid rod. Moving right along to section 2, the thermal growth twist. But here is the plot twist of our story. We aren't building giant steel sculptures here. These pipes are carrying boiling liquids and superheated steam. And as we all know, when metal gets hot, it expands. Now, what's really interesting about this slide is what happens to our cheap, reliable rigid support when the heat actually gets turned on. In the installed position over on the left, the pipe rests perfectly on the support. Looks great. But look at the operating position on the right. Because of the vertical growth of the piping system, specifically that differential thermal growth between the structure and the pipe itself, the pipe actually lifts right off the support, just completely separates. So suddenly that support is carrying absolutely zero weight. And honestly, this is physically catastrophic. Think about it. If the pipe lifts off the support entirely, all of that massive dead weight doesn't just disappear. It has to travel elsewhere in the system, loading up other areas that definitely were not designed for it. Or conversely, what if the rigid support is actually holding the pipe down from the top? Well, as the pipe tries to grow upward, the support stubbornly fights back. This causes extreme bending that can severely overstress the elbows of the pipe. And all the while, the loads on your main anchors are increasing drastically well beyond just the basic dead weight. So clearly, this cheap rigid rod is completely unsuited for a hot thermal system. Which brings us to section 3, pulleys and counterweight fixes. So engineers had to go back to the drawing board. If a rigid support won't work simply because the pipe moves, we obviously need a support that can move with the pipe while still carrying the exact same amount of weight. And on paper, this first attempt looks like absolute genius. It's a basic pulley and a counterweight that perfectly matches the dead weight of the pipe. If the pipe heats up and moves vertically, the counterweight simply drops a little bit. If it cools down, the counterweight goes back up. It's that simple. No matter where the pipe moves vertically, this system always supplies the exact consistent dead weight load to that specific point on the pipe. In fact, the piping code even explicitly allows for these counterbalance supports. But, as you might guess, this perfect fix has some pretty fatal flaws out in the real world. Just think about the poor steel structure on the ceiling that's holding this entire pulley system up. It now has to carry 2 times the dead weight. It has to hold the weight of the actual pipe and the weight of the massive counterweight block. That's a huge structural penalty. Plus, out in a gritty, dirty industrial environment, pulleys require a ton of maintenance over the years. You're introducing a severe risk of mechanical breakdown, friction, and wear. So yeah, we definitely need something more compact and reliable. All right, section 4, constant effort hangers. This brings us to a highly mechanical escalation in our quest to perfectly support this moving pipe. Take a look at the internal mechanics of this Grinnell constant effort hanger. Now, unlike a giant dangling counterweight, this unit uses an enclosed load spring, a pivot, and a series of mechanical links. And this brilliantly illustrates why it's called constant effort. It's all about that internal geometry. A very short compression in that powerful internal spring translates into a much larger deflection at the free end that's holding the pipe. It basically mechanically softens the entire setup, giving the pipe a huge range of vertical travel without fighting back.
So the crucial point is how we actually define constant here. Because the spring is technically moving, the load absolutely must change a tiny bit, right? That's just physics. But industry standards dictate that a constant effort hanger must maintain a load variation of no more than 6%. That means from the type's lowest point all the way up to its absolute highest thermal expansion point, the amount of support it receives changes by a maximum of just 6%. To put that into perspective, if your minimum load is 1,000 pounds, your maximum is just 1060. For all practical engineering purposes, that effort is constant.
But, if they work so incredibly well, why don't we just see them everywhere? Well, remember our economics slide from earlier? These things are massively expensive. We're talking 3 to 4 times the cost of a simple rod. But beyond just blowing the budget, they are also prone to something called position drift. In high-temperature systems that operate in what we call the creep range, if you don't calculate that initial load absolutely perfectly, the pipe will start to carry some of the load away. The system will start to drop, and eventually these expensive hangers will completely bottom out. And finally, all those cool pivots and links, well, they have internal friction. This causes a kind of stickiness that requires a sudden jolt or change in force just to pop the mechanism free. Moving to our final chapter, Section 5, the spring solution. We really need a final resolution here that sits right in the Goldilocks zone of our engineering puzzle. Not too rigid, but also not too complicated. Let's move to and see how this builds perfectly on what we've covered so far. On one extreme end of the spectrum, we have the rigid support. It has incredibly high stiffness, but it literally breaks the system when things heat up. On the exact opposite end, we have constant force supports, like those counterweights or the mechanical hangers. These effectively have no stiffness at all, but they are incredibly expensive and a total nightmare to maintain. So is there anything that lives right in between these two extremes? Well, yes, there is. Meet the absolute workhorse of the modern industrial plant, the variable spring hanger, or as it's often just called out in the field, a spring can. It has what we call finite stiffness. This is our practical, economical middle ground. It allows the pipe to travel vertically as it heats up, all while safely managing the load. Now, because it's just a variable spring, as the pipe moves up or down, the load actually will be a little bit different at every single position. But, and this is key, unlike a rigid rod, it gives way just enough to prevent a total disaster. Best of both worlds, right? Now, here's the catch. Because the load on the pipe actually changes as that variable spring compresses and decompresses, we can't just eyeball it or guess which spring to buy. Instead, we rely on some seriously sophisticated pipe stress analysis programs like Caesar 2 software. What the software does is calculate the exact acceptable load imbalance that the actual piping elbows can handle safely. It then automatically scans through massive global manufacturer catalogs to select the perfect spring with the exact right short, mid, or long-range spring rate for that specific node on the pipe. It's essentially high-tech software stepping in to optimize a highly physical, old-school piece of hardware. And honestly, that brings us full circle. Next time you walk through an industrial plant, or even just catch some footage of a refinery on TV, I want you to look up. Are you just going to see a simple piece of metal holding up a pipe? Or will you see this massive hidden battle between physics and economics? Because every single support you see up there is a deliberate, highly calculated choice between rigidity, thermal growth, constant effort, and the elegant compromise of a variable spring. Thanks so much for joining me on this explainer, and keep looking out for all that hidden engineering in the world around you.